Okay, second part of lesson 15 on Taylor and Maclaurin polynomials. This part is going to focus on the remainder. This is something that is tested when they ask about Taylor polynomials in free response. They tend to ask about a Taylor polynomial, and then a follow-up question is about the remainder. So we need to talk about how to do these, but also how they're going to want you to write them. So when I've looked over free response questions and answer keys, they like that notation. So the remainder basically is, this is my best explanation for it. If I were writing a Taylor polynomial to estimate a function, if I could keep the Taylor polynomial going on forever and ever and ever to infinity, then that Taylor polynomial would be an exact match for the function I'm trying to estimate. But that's not reasonable. I can't keep this going on forever. I've got to stop somewhere. So if I were to stop at the third term, then everything that came after that term would be the remainder. That's the error. That's the part that got left off. What if I were to stop after the fifth term? Well, then the sixth term would be the one that's the remainder. What if I stopped at the 10th term? Then the 11th term is the one that's the remainder. So basically, I'm going to do a polynomial for a little while, and then I'm going to get tired of that, and I'm going to quit. And if I quit whatever term I quit at, the next term after that is the remainder. So writing the remainder with this notation is called the Lagrange form of the remainder. So when you see Lagrange, I've heard it pronounced both ways. When you see that term, then that's what it's asking for. It's asking you to write the remainder in that form. And I'm going to do that on the homework, so you need to be familiar with that. So how do you do these problems? Well, here's some interesting reading that you can read later. So what are we really looking for? When we're looking for the error or how accurate something is, or trying to think of words that they're going to use for the problems, we're trying to figure out, okay, this is what I think this value is, but how far off could I be? And when I'm asking how far off could I be, I want to know the maximum. Don't tell me the price of something and say, it's within a couple dollars of that, when really it's $10 more. I would rather you tell me that it might be off by $10 and it really only be $2, instead of telling me that it's off by $2, but then it ends up being $10. So I want to know the maximum. Tell me the worst case scenario. If this is the worst that it could possibly be, how bad is it? So the reason that that's important is that's going to make sense when we're talking about something later on. I'm wanting to know the worst. Give me worst case scenario. What is the worst error? What is the most that I could be off? What is the most I could have missed this estimate by? So I've got a third degree. I want to estimate sine of 0.1, and I want to know how far off I might be. I'm not asking you what is the sine of 0.1. I'm asking you, if I do a third degree Maclaurin, how far off could I be? How accurate is this? What is the possible error? What is the maximum error that I could have if I do a third degree? And in the real world, if I'm not okay with that amount of error, then I don't need to do a third degree. I need to do a fourth degree or a fifth degree or a sixth degree. What if I plan to do a fifth degree and the error was like super, super tiny, and I'm like, well, I don't need it to be that exact. I don't need it to be accurate to 5 decimal places. I only needed it to be accurate to 3. Well, then I don't have to do that many terms, and maybe that saves me some time and some work. Okay, here's how this goes. You're going to write your polynomial the same way that you did before. So we're going to find, this is Maclaurin, so it's centered at 0. So I'm going to find f of 0. I'm going to find the first derivative at 0, and the second derivative at 0, and the third derivative at 0, and then I'm going to stop because it said third degree. So I found all my derivatives, and then I write my equation. the third one over 3 factorial x to the third. Okay, the second one was 0, so none of that. Plus the first one over 1 factorial x to the first, and then my constant was 0, so that's not there either. So my P3, my Taylor polynomial, Maclaurin polynomial, third degree, is negative 1 over 3 factorial x cubed plus x. So where does the remainder come from? The remainder comes from the next term. So if my polynomial accounted for the first 3 terms, then the error is the fourth one. So the remainder for the third term, the error for the third term, is whatever the fourth one would have been over 4 factorial x to the fourth. The error is the fourth term. Okay, well, what would the fourth term have been? It would have been the fourth derivative. Okay, hold on, let's back up. My third derivative was negative cosine, so what's my fourth derivative? Well, the fourth derivative of negative cosine is sine, so here's my fourth derivative, 4 factorial x to the fourth. Here's where that part I was talking about before comes in. I want to know the worst case. What is the most error that this could possibly have? Well, the part where that comes from is this part. How big could that function possibly be? What is the maximum value for that function? Well, I mean, I know sine only goes from negative 1 to 1, like ever anyway, because I know what the graph looks like. But also, think about what part of the graph we're looking at here. I'm centering this at 0, and I'm estimating at 0.1. So I'm really only interested in what's going to happen between 0 and 0.1, between the point where it's perfect and the point that I'm estimating. Well, when is sine going to be the biggest? Sine is going to be the biggest at 0.1, because let's see, sine at 0 is 0, and then it starts to go up. Okay, well, what is sine of 0.1? Because that's the biggest. Oh, yeah, wait, I don't know, because I don't know sine of 0.1, because that's not like a number on my unit circle. I don't know it. Okay, well, what else do I know about sine? The biggest it could possibly be ever is 1. So the biggest this term could ever be is 1 over 4 factorial x to the fourth. Sine might be less than 1, and then that would be okay, but the worst case scenario is this. Okay, so now what is that error at the point that I'm trying to estimate? So basically what I've done is I've written an equation for the error. Now I need to actually find the error. So here's my equation for the error. And when I plug in 0.1, I find out that the most the error could be, the absolute worst, is 0.000004. So when I use this polynomial and I plug in 0.1, the value I get from P3 and the value I get from the original function are going to be within that much of each other. That's pretty impressive, really. That I could turn a trig function into an algebra equation with only 4 terms, technically because it's P3, and it is that accurate. So that's how you find the error. And it's like they can change up the wording and how they ask the questions, but it's pretty much always going to be that way. So if you guys look at this one, what is the largest possible value for, it's not asking you the value for the error, it's asking you the value for 1 over square root of e. Okay, I have no idea what 1 over square root of e is, but I'm going to use the function e to the x to estimate e to the negative 1/2. So, but I don't know how to do e to the x. I don't know how to do that off the top of my head. Remember, this was all done a long time ago. So they were working this out with no technology. I mean, the technology they had was a quill and ink. So we can type it in the calculator, but like, how does this work? What's really going on with these things? Okay, anyway, so I need to take the function they gave me. I need to turn it into a Taylor and Maclaurin polynomial. We want to estimate e to the negative 1/2. Negative 1/2 is pretty close at 0, so I'm going to center this at 0. So I need to find f of 0. I need to find f prime of 0. I need to find the second, the third, the fourth derivative at 0. And what you notice with these is the derivative of e to the x is e to the x, and I'm plugging in 0. So all of these derivatives are 1. 1, 1, 1, 1, 1, 1, 1. So I get 1 over 4 factorial x to the fourth, 1 over 3 factorial x cubed, 1 over 2 factorial, 1 over 1 factorial, and then my original value was 1. So there's my polynomial. Okay, this polynomial, if I plug in negative 1/2 right now, that's going to give me the Maclaurin polynomial estimate. If I were to plug in negative 1/2 for all of these x's, that's going to give me an estimate for the function value. And I'll go ahead and tell you now, since it's down here later, if I type that into the calculator, I get 0.60677. So that's my estimate for e to the negative 1/2, 0.60677. But we know that's not perfect because the polynomials and the functions may be incredibly close, but they're not necessarily exact. So what's the possible error? Okay, wait, we want to know the maximum value, so I want to know what is the most that the error could be. What's the biggest value that I could have for the error? Well, I did a polynomial degree 4, so where's the error come from? It comes from term number 5. So I need the fifth derivative over 5 factorial x to the fifth. Well, how big could the fifth derivative be? You remember our derivatives up here? What was the derivative for the first derivative, second derivative, third derivative, fourth derivative? Anybody want to guess what the fifth derivative is going to be? Well, it's going to be 1. So the fifth derivative is going to be 1, and 5 factorial is 120. So here is my error. So what is the error when x is negative 1/2? If I plug in 1 over 120 times negative 1/2 to the fifth, I get 0.0002. Technically negative, but it's always plus or minus. So my function told me that this is the answer. My error told me, okay, but it might be a little bit more than that for real. Like our estimate's good, but our estimate might be off by 0.0002. So the real value of 1 over e to the square root of x has to be less than our estimate plus our error. So I think 1 over square root of e is 0.60677, but I know for sure, no doubt, I know for sure that 1 over square root of e is less than or equal to 0.6069, what my polynomial said, plus the error that might be there. Those are AP questions. That is an AP free response question, something similar to it anyway, from the past. This one, similar thing, I'm going to try to go through this one faster. Function value, first derivative, second derivative, third derivative. So here's my polynomial. And I want to show that the error is less than 1 over 100. So if there's my polynomial, where's the error going to come from? It's going to come from the fourth derivative. So I've got the maximum. How big could the fourth derivative be? 4 factorial x to the fourth. Okay, this is where you got to think. When I'm dealing with a cosine function, it's centered at 0. It's going to go to 1/3. So on the interval from 0 to 1/3, where is that going to be the biggest? Well, remember what cosine graphs look like? Where is cosine the biggest? It's the biggest at 0. So if I were to plug 0 in for the x, that's going to give me the maximum value for this function. So if I plug in 0, 2 times 0 is 0, plus pi over 6 is pi over 6. Cosine of pi over 6 is square root of 3 over 2, times 16 over 4 factorial x to the fourth. So, got a whole lot of scribbling here that whole lot of scribbling here that I need to get rid of. So this simplifies to here. That's the absolute maximum value that the error could be. Okay, well, I don't want the error anywhere. I want the error at 1/3. So if I plug in 1/3, that works out to root 3 over 243, which is less than 1 over 100. So y'all all know root 3 over 243 is less than 1 over 100, right? Well, probably not. But if I were to multiply this by 2.43, that'd be 243. So this would be 2.43, and root 3 is like 1.7. So 1.7 over 243 is less than 2.43. Anyway, that's true. It is less than. And that's the super important stuff you guys need to know about this. So here's another example y'all can look over later. I'm going to stop the video now, and I'll do another one over the homework later.